All right. To my knowledge, my goal is to get this chapter in before your final exam. That's my goal. Why? This is the last chapter that is strictly pre-calc only. Starting with the next chapter 5, that's when we go pre-calc and trig. That's when things get fun. I like things that are fun. It's very exciting. So inverse functions. I'll tell you what little bit I know about inverse functions, which is usually a lot more than most people. An inverse function is written like this. If that's a function, the inverse is written like, the inverse is written like this, f of -1 of x. That means inverse. On the flip side, that means reciprocal. Not even close to being the same thing. One means reciprocal, one means inverse. And, yes, this came up as a legitimate complaint and argument. You said this meant inverse. I said, no, that means the function value of 1 over x. It matters where the -1 goes. If you want to apply it just to the x, you put it just to the immediate upper right of the x. Apply it to the function immediate upper right of f. And if you want the reciprocal, you just put 1 over the whole thing. Fantastic. All right? This is weird. I haven't been in my room all day today teaching. All right. So I'll give this a shot. It's kind of weird being in here. I should be like somewhere else. Are you ready? Yeah.
So is that the inverse right there that you just wrote?
This is the inverse right here. That is the inverse. Okay? Do you know what inverse means? It's where you switch x's and y's. It's where you switch x's and y's. All the y's become the x's, and all the x's become the y's. The domain becomes the range, and the range becomes the domain. The square roots become the squareds. The additions become the subtractions. It's really quite a lot of fun. That's the world of the inverses. In fact, on your calculator, you have a button that says sine of x. Above it, you have this. That means the inverse of the sine of x. All the y's become x's, all the x's become y's. Everything upside down becomes right side up. I love the world of inverses. I think we have enough information to go on and see what's next. Oh! A one-to-one function. What's a one-to-one function? We've talked about this 3 times to my knowledge. This will be the 4th. First of all, what's a function? F of x passes the vertical line test, right? Vertical line test. What do you think one-to-one means? Horizontal line test if you're talking graphically. Graphically speaking, it passes the horizontal line test. That means y is used once for every x that is used. You can only use y once. Once y is used, it can no longer be used again by any other x value. X's can be used for the entire domain. So, a Venn diagram of this would look like 1-to-1, 1x, 1y. A function can look like this, 1x and another x to the same y. That's still a function. For instance, x squared. If y equals x squared, that is not 1-to-1. Because if x is 1, y is 1. If x is -1, y is 1 still. That is not a 1-to-1 function. It's still a function, just not 1-to-1. So if something is a 1-to-1 function, it has an inverse. If something is not a 1-to-1 function, it doesn't have an inverse. Oh, don't be fooled by the following. If I say y equals x squared, semicolon, x greater than or equal to 0, what do you think that means? Yeah, exactly. It only means part of the parabola. Is that now one-to-one? Yes, it is. You can take any function you like and modify it to become one-to-one. In doing so, a lot of functions can be one-to-one if you modify their domains. That is a very common mistake. People see the x squared, think it's not one-to-one. But you need to look for the domains being modified. And that's the case. What is this down here? Number 1 and 2. That's the algebraic definition of one-to-one. The horizontal line test, that is the graphical definition of one-to-one. This, the algebraic definition of one-to-one. This being the Venn diagram definition of one-to-one. Why so many definitions? Easy. When you get to calculus, there's another definition of one-to-one using derivatives. Okay? A lot of definitions try to get the point across. Things are really cool when it's one-to-one. If it's one-to-one, and I said all the x's become y's, if 2 4's on the function, what would be on the inverse? 4 2. That's really cool. We just made some oh, that's not. What is that? 0 4. How about this? 4 0. That would work. We just made a bunch of kaleidoscopes in my sketchpad lab before lunch. You make these pentagons, hexagons, you start reflecting over all these lines, you move it, everything spins in uniformity. It's great. This one is reflected over the line y equals x. We haven't had a function symmetric over the line y equals x yet, have we? Over the y-axis, what type of function is it? Even, odd, or one-to-one? Any function symmetric over the y-axis. What type of function is it? Even, odd, or one-to-one? It is even. Any function symmetric over the origin is what? Odd. If you take these functions and you map them over the line y equals x, then they become one-to-one. That's how it works. That's what the inverse looks like. So if I have like a little, squiggly line, like that, oh no, I just made it up. Then the one-to-one function will be something like that. They're reflections. That's what our class lab was, reflections. All right. Oh, no, this class doesn't get a video. Never mind. Moving on. I meant for Monday. We already talked about the horizontal line test. If a horizontal line hits the graph in 2 places, it is not one-to-one. How do you fix that? You modify the domain. Okay? How much? Do you modify it? No, just depends. Usually they modify it for you. You don't have to modify anything. Let's get to the problem, shall we? All right. This is how you find an inverse. That's their definition of how to find an inverse. My definition of how to find an inverse is when the domain becomes the range. Domain of f of x becomes the range of the inverse of x. That's one thing about the inverses. The domain and the range switch. And the range of the inverse becomes the domain, the range of the function becomes the domain of the inverse. I don't know where I saw that, but I saw it one time and it's stuck ever since. That's true between domains and ranges. The y's become the x's and the x's become the y's. It's really a great relationship when you're a function and you're one-to-one. For every x and d and every y and r. Yeah, that's a really technical way of putting it. Y equals f of x if and only if x equals g of y. Yeah, that's pretty much the same thing. All right? Now, one more thing. If I have a function f of x with a point x and y on it, That means on the inverse, they switch, right? Because the domain becomes the range, and the range becomes the domain on the inverse. That's how points work. You remember the point 0, 4 we had? It became 4, 0. Okay? Let's give this a shot. If this is the function for t, okay, this means the points on here are 0, 2, 3, 5, and 5, 6. If the function is 1 to 1, which it is, no y is used twice, no x's are used twice, therefore it's a function. No y's are used twice, therefore it's 1 to 1. What would be the points on the, if this is on the function, what points would be on the inverse? 2, 0, 5, 3, and what? 6, 5. So the question asks, what is the inverse value if x is 5? So if I put in 5 for x on the inverse, what's the y going to equal? 3. Right? This means on the inverse, if x is 5, y is 3. Okay? Because we're looking at the inverse. Okay? Let's see what's down here. The inverse, oh, now wait a minute. Aren't the two y's being used? One y is being used twice. So therefore, there can't be an inverse. Do you see why? If you went the inverse value of g for 6, you'd have two answers, 2 and 4. And that wouldn't be a function, would it? The inverse wouldn't pass the horizontal or vertical line test. So while these points work great on the function, f of x, 1, 3, 2, 6, 4, 6, on the inverse, you can't have, the 2x values, 6, 2, and 6, 4, and 3, 1. You can't have that. It would not be a function. Okay? Therefore, it wouldn't exist. Does not exist. All right, is it time for a break? I think we'll go ahead and give it a shot now. It looks like Bo could use a break. All right. Let's see. Oh, this one is brand new. I don't think we've done this one yet. If you're competitive, you need a competitive partner. If you're not competitive, it doesn't matter. Yep. No.
Well, I request that we play as a group and we play.
Okay, but we're not playing BizBuzz today. What did I say we were doing?
I don't know. You said it was competition.
You said a new, and we needed a partner.
New with a partner. Oh, competitive. All right, yeah, here we go. Everybody up. Oh, your partner. Well, you can make do. Well, who's Elizabeth's partner? I know, but when she's here. Oh, look at Kyle. He has no partner. Rachel. What about?
We can have a group of 3.
Okay, group of 3. You'll rotate in. Here we go. All right, player A. Player A takes their right hand, extends it, and places it over their left forearm like this. Okay? Now bend your elbows slightly so you're relaxed with your hands sticking out like this. Good. Player B, you grab a hold of the hands. Now you can do this, I think. I think so, yeah. Try it 3-way. I think it'll work. Then player B grips it for a thumb war. No, that's not how you grip it for a thumb war, like that. No, not you. There you go. There you go. No, only one of you have to do that. There you go. You're right. Good. Now you grab a hold of those two. And then you guys will have to go upside down. All right, ready? Now you have a thumb war. You just need one thumb. 1, 2, 3. I declare a thumb war on you. Go. Both hands at once. Now you try to... Now when you're done, you reverse. So player B then is crossed and player A is not. All right. All right. Okay. All right. Everybody watch the group of 3 going at it. Ready? Go ahead. All right. Nice job. Have a seat. All right. That's why we need somebody competitive with somebody else. So, E and Stephanie and Chase, you guys can do that on your own. And, all right, we'll keep going. In this one is graph A. You don't need to write this down. Is graph A 1 to 1? No, it's not. It is x cubed, and it is not 1 to 1 because it doesn't pass the horizontal line test. What about B?
Yes.
Yes, it does. I said you don't have to write it down. Yes, it does pass the horizontal line test. C, is that a 1 to 1 function? No, it doesn't pass the vertical line test. It's 1 to 1, but it's not a function. So, in that case, that wouldn't do you much good either. So this one does not pass the vertical line test. Ghostbusters. This one doesn't pass the horizontal line test. Okay, there we go. And this one doesn't pass the horizontal line test. This one's yes. There we go. All right, good. Yep.
So it has to pass both of them.
It has to pass both of them to use the phrase 1 to 1 function. All right? If it's a 1 to 1 function, it has an inverse. The inverse, the domains become the range, and the range becomes the domain. All right? Whoever did the thumb war with Lou did some damage because Lou is still like practicing or something. You practicing for the next round? Oh, okay. Okay.
She was playing when I was winning because she needed me.
Oh. These are just FYI facts. It should be common sense. A function is increasing throughout its domain, it's 1 to 1. If it is always increasing, it's 1 to 1. If it's always decreasing, it's 1 to 1. That just has to make sense because if it's always decreasing, there's never a place where it can turn and come back up, and then that wouldn't pass the horizontal line test. Anyway, that's just a couple of those FYI notes we throw in there, mainly for calculus because we're always trying to find the increasing and decreasing domains. Today's Friday. They have that one question quiz today. I'm very excited about that. One question. All question? How long? It takes them a little bit of time to do it. Some won't finish. Yeah, pretty much. Well, the ones we're doing now, it takes like half an hour problem. All right. Is this function 1 to 1? Why?
It's a point. No, it's not. It's a line.
That's not a line. That's a rational algebraic function. We did those last chapter. What is the vertical asymptote? At x equals 2? 1, 2. Doesn't work? I don't know. Is the function always increasing? How do you tell if it's always increasing or decreasing? If I put in a number like 10, it's going to be positive. If I put in like a negative number, it's going to be negative. No, it doesn't cross. It has a y-intercept at x. Negative, well, I meant x. So it goes like this. And then it goes like this. So is that graph always decreasing?
No.
Why not?
This is the increasing part of that.
Well, I mean, if you're going from left to right, you're assuming this is probably getting closer to 0, isn't it?
Mm-hmm.
So it's always decreasing? And what about this one? Always decreasing. I guess where wouldn't it pass a horizontal line test at?
Everywhere. It never yes.
It never what? Oh, no, it can't touch the horizontal line on 0. Oh, yeah, because there's no x-intercepts. Okay. That one looks like it's always, yeah.
When we were talking about the domain increasing and decreasing, is it one or the other always?
Mm-hmm. If a function's always increasing, then it's 1-to-1. If a function's always decreasing, it's 1-to-1. In this case, f of x is always decreasing for all x from negative infinity to 0, union 0, oh, sorry, 2. Negative infinity to 2, union 2 to infinity. It's increasing for all x. That's in that set. Okay? That's just how you'd write the statement. How do you know if it's not decreasing? It'll show up, I think, if it's not decreasing or increasing. But I think in that one, I think it always is. What about in this one? Yeah, it was. Okay? So that one is 1-to-1. So yes, it is. This next one is the function 1-to-1, the cube root of x. The cube, well, first of all, at 0, it's going across. What's the cube root of like negative 27? Negative 3. And then the cube root of 0 is 0. And the cube root of 27 is 3. So I think the function is always going to look like this. So it's always going to be increasing. Yeah, it makes sense. F of x is always increasing. Yeah, the domain for all x in the set from negative infinity to infinity. Okay, for all real numbers. Yeah, that would work. We haven't talked about limits yet, so we'll do that later. Well, this one. Is it 1-to-1? Easiest way to look at it is with a graph, isn't it? You have a calculator? Take a look at the graph. Somebody says no. Why no, Sam? Nice guess. He's actually right. Doesn't pass the horizontal line test. Nice job. If you graph it out, looks something like that. So you can determine, you can say no. That is not a 1-to-1 function. Oh, remind me after I'm done recording to show you something. All right? It has to do with presents. Moving on.
Like presents or like
Presents.
Gifts like
Gifts to me from students. Theorem of an inverse function. Let f be 1-to-1 with a domain D, range R. If G is a function with domain R, range D, then G is an inverse of f if and only if the following are true. What does all that mean?
I don't know, you tell me.
Oh, I know. This is the first textbook that in calculus, they use this all the time. I was talking to a gentleman from Rantoul, top 80 years, I think. You remember I told you this was f of x. The inverse was this, right? In this textbook, they also use g of x. That is very calculesque to identify the inverse. Yeah? And they have to do this because of all the external notation you have in calculus. You can't handle a negative one with everything else you have to write. So I had to come up with another way. So he said from now on, G is the inverse of F. Okay? Now, what this means is if you take the composite function, the inverse of the function, and you put in, the composite, the inside function and the inverse, you should come out with an x. And also, the function compositely formed with the inverse should also equal x. So if you take entire functions and put them into each other, you should come out to equal x. Then, it's an inverse. Guaranteed. If you have two equations, you're not sure if they're inverses of one another, you do composite arithmetic, and then you come out with a solution x, then it's true. Both directions. One for the inverse, and then one with the function. That's hard. There's another way of doing it, but like I said, that's more in calculus, where they use the g of x notation. But in this book, they'll use g for the inverse function. They started doing that because of some problems they had in differentiation rules with the inverse and the g and things like that. So, in this case, aha! Look at this. X squared plus 5. What's the graph look like? It's a parabola, opening them up with a y-intercept of 5 and a restricted domain, correct? It looks something like this. Oh, then the negative square root of x minus 5. Wait a minute. What's the square root function look like? Yeah, it's like a parabola. And this 5 is moving it which way? To the left or to the right? To the right 5. And this negative flips it over which axis? The x-axis. Woohoo! Looking pretty good. See, if you got nothing to do next week during the holidays, graph some inverse functions and share them with people.
Okay.
I do. I do. Here you go, kid, go play this for a while. Great, thanks, Uncle Mike. And then off they go. The joy math brings. All right, ready? So f of g of x. Remember, this means the inverse. Now, why don't they say that? They're trying to get you used to the next book you're going to use. It's purple. They're trying to get used to it. Some of you, not all, some. All right, there's f, there's g. So let's do this one. F of g of x first. Okay? So that equals something squared plus 5. Correct? What's wrong? Obviously doing something. Negative square root of x minus 5. What happens when you square that? What do you get? Close. The negative turns to a positive, and the square root turns into a single power, so you're just left with the expression x minus 5. Okay? Plus 5, so you end up with x, which was the plan. Graphically speaking, I could probably tell they were inverses of each other. Now, I have to do g of f of x. Why wouldn't you? That one works. And the theorem says it has to be both. Excuse me? I don't know. Well, I don't know. What's the square root? Oh, I can get rid of the parentheses, can't I? So I can be a 5, right? So I have the negative square root of x squared. Oh, yeah, but actually, don't forget, this x is actually negative. Some people put a negative right here in. Because negative x times negative x is x squared, isn't it? Some people do that little trick right there, so when they get to the end, there's no problems. Interesting, don't you think?
How?
Well, some people don't put the trick there, and they just theorize it. Let's not put the trick in there, and let's just work with it as is. Okay? So what is the square root of x squared going to be? X. What is x in the picture? Is it positive or negative when you're talking about the function? Negative. So two negatives make it a positive. Okay? Either way you want to look at it, the negative x is going to show up. How do you know that? It said all the x's are negative. Sure. Yeah, that's a pretty cool problem. So it works both directions. Yes.
Couldn't you just again arrange a number for x and y the equations?
You could, but that doesn't always work. Okay? I was just following the actual factor or the actual inverse theorem. All right? Let go.
So like when it's f of g of x, you're looking at the graph g of x, and then we're looking at g of f of x, looking at f of x.
Yeah. Well, yeah, you're looking at both of them because they're trying to get up on this line x, which is kind of cool. So you're saying that y equals x equals y. That's a common theme with inverses. I don't know. We've already discussed that, haven't we?
Yeah.
The domain and the range. Excellent. I think I'm about done.
No homework.
Homework?
No,
Said no homework.
Oh, there is. I'm not even done yet. That's how I'm about done. Oh, here is my domain. Is what? It says determine the domain and range without actually finding the function. In other words, make yourself look intelligent, like you've done a lot of work in your head, then come up with the answer and people will be impressed. What is the domain of the function? X cannot equal negative 3. Very good. So therefore, what is the range of the inverse? Y cannot equal negative 3. Woohoo! Oh no. Halfway there. What is? Wait a minute. This equates to the vertical asymptote, doesn't it? This equates to what? A horizontal asymptote, doesn't it? What's the horizontal asymptote of the original function? Y equals 0. Do you think y can ever equal 0 looking at the equation? You think so? Well, if you think so, set it equal. Y equals 5 divided by x plus 3. Cross multiplying, what do you get? 0 equals 5. Is that a true statement? So y cannot equal 0. So what do you think the domain of the inverse is? X cannot equal 0. There's a lot of math fun facts floating around every single problem. My job is to allude you to that fact so you become more aware and have more attention to detail. How's it going with the detail? Pretty good? Nice. Is it time to move on? Oh, yeah, I'll go a couple more minutes. And then, what time we got here? 12? I'll go a couple more minutes and I'll tell you my, show you the presents. Okay? You want to try this one on your own? No? Sure you do. Oops. What's wrong? Who? So, this is a fun day. What is the domain? X cannot equal what? Negative 1/9. So here, y cannot equal negative 1/9. What's the range? Very good. Y cannot equal 2/9. If it could, set it equal and solve. 95% of the time, I'd say. You're not going to equal the horizontal asymptote. So in this one, x cannot equal 2/9. How'd that go? Pretty good? Fantastic. How far did we get? Perfect. Yeah. So what page are we on? 288. 1 through 23. Odd. You know, the fun thing is that I will tell you all about the presents I got. You won't believe it, but I got